Alrighty, so we're going to start into quantum mechanics, the study of quantum mechanics, by discussing the most famous quantum mechanics equation, I think most people have heard of, which is Schrodinger's equation. Schrodinger's equation is that formula, it's an equation, it's a differential equation, which helps to model quantum systems. It was developed, obviously, by Erwin Schrödinger. And what you're going to find when you discuss and you study quantum mechanics fully is that it's not the only way of doing quantum mechanics. There's actually multiple systems that are kind of independent from each other that all allow you to study quantum mechanics with their own version of equations, their own version of how to do things. And Schrodinger's equation, Schrodinger's method, is one way of doing it, and it's usually the way taught from the beginning because it's the easiest one to get into. It's not necessarily the most efficient or the best. All the methods have pros and cons. For instance, there's another method, Heisenberg's method, which deals with matrix mechanics, and it has its own ways of doing things. And a lot of times it's better than Schrodinger's method for certain problems, but for others it's not as good. So Schrodinger's equation, this method will be the way we're going to study from the beginning. It allows us to get into the topic fairly easily and to actually work some problems. So how do we get to it? Well, first of all, you have to know that Schrodinger's equation is really conservation of energy. At its heart, it's a quantum mechanical form of the statement of conservation of energy. And if you remember what conservation of energy really says, at its most basic, it's mechanical energy. It says kinetic energy plus potential energy is equal to a constant. That constant is just called the total energy. Right? You have a system, you measure at a single point in time, how much kinetic energy does the system have? How much potential energy does the system have? You add it all together, and that's the total energy of the system. And then, once you know this number, then you say, at any time, no matter what, as long as the system is closed off, I can measure, I could wait 5 seconds, I could wait 10 years, and go back, and I guarantee you the total energy will be the same. The only way it won't be the same is if it's affected by outside systems. Now, the kinetic energy may be different, or the potential energy may be different, but if I combine the two, add them together, the total energy will be the same. But what you're going to find is that in quantum mechanics, math is done a little differently. We remember that kinetic energy is 1/2 mv squared, and potential energy, well, that depends. It might be mgh or 1/2 kx squared, or all sorts of things, depending on the system, depending on what's affecting it. Is this heat potential energy? Is it electric potential energy? Spring potential energy? All these things. But you add all the potential energies up, that's potential energy. Now, we need to discuss the mathematics of quantum mechanics because, as I said, it's different than what we're used to. When you first started learning physics, of course, you knew about numbers, scalars they're called, and you were able to do addition and subtraction and multiplication of numbers, and you learned this all the time from the very beginning of school. And then you got into physics, and all of a sudden you were talked about vectors. And vectors, was different in that the math for vectors wasn't done the same way. If you wanted to add two vectors together, it wasn't just like adding two numbers. You had to, first of all, if the two vectors were in the same direction, you can add them. But if they weren't in the same direction, then all of a sudden you had to go through this long method of find the components of the vectors, add them component-wise together. Then you have the new components, and you combine those components together by Pythagorean theorem or whatever, and you get a new magnitude and direction of the vector. It was different than before. Well, similarly, in quantum mechanics, there's a new method for doing things as well. Now, the big thing to note is for quantum, the main equation is a differential equation, which means it's not just like a basic, F equals ma, or kinetic energy is 1/2 mv squared. Those can be written as differential equations. If I wanted to, I could say F is equal to m times the second derivative of position with respect to time squared, and now I have a differential equation there. Or kinetic energy is 1/2 m x dot squared. That's a differential equation. But usually, when you're first learning physics, you learn the equations without thinking of them as differential equations. However, as you go more and more into physics, you study it more in depth at higher levels, differential equations become more important. They're more powerful, they allow you to do more, but at the same time, they're harder to solve. Well, in quantum mechanics, the big equation you're going to work on is a differential equation. So we need to build this differential equation from conservation of energy. And to do it, I need to tell you about what's called an operator. Operators are going to be things in the math of quantum mechanics which are new. These are the things that make doing quantum a little bit more difficult than just straight up solving equations. But once you get used to them, it's not a big deal. Operators act on things. Obviously, they operate on things. The easiest one to see, for instance, is the position operator. The position operator is called X, and sometimes they put a little hat on top to denote that this is the operator. This is not the variable X, this isn't the letter X, this is the operator X. And what does it do? Well, for this particular operator, when I operate with X, so let's say I'm going to operate with X on a function, let's call it F, then it does something. It's a symbolic thing, so it may mean multiple steps. It may stand for some long method of doing a whole bunch of different things. But for the position operator X, all it means is you take the function, whatever it was, and you multiply by the variable X. So that's very nice. It makes sense. When we see X times F, where X is the operator, what we need to understand that it means is take the variable X, the position, and multiply it by the function F. It's exactly what you would hope for it to mean. So that's really good. However, this is not true of all operators. Different operators necessarily are done differently. The next one, which is most important, is called the momentum operator. And that's P. Remember P, the momentum is mass times velocity in physics. Well, the momentum, instead of being a variable, is an operator in quantum mechanics. It operates on an object. So, what does it do? If I take the momentum operator P and I apply it to a function, let's call the function psi, Greek letter psi, what does it mean? Well, this is much more complicated than the previous one. This does not mean take the variable P and multiply it by psi. It does not mean take the mass times the velocity times psi. What it means is the function will be operated on by an operator, which is negative I h bar, which for now, don't worry about what those mean. And then we take the derivative with respect to the position of psi. Okay? So a few things, just to make sure we understand. This symbol here is called the partial derivative. Obviously, you've seen d by dx like this, which is the total derivative. Well, the partial derivative is just like the total derivative, but when we're talking about functions which can be of multiple variables, so for instance, psi could be a function of x and y. You know, it could be 4x plus 2y squared, let's say. So psi has x's and y's in it. Well, when I take a derivative, I need to know, am I taking a derivative of this function with respect to the x or with respect to the y? Does the x depend on the y? All these types of things matter, and you learned this in calculus. You learn it in multivariable calculus, or sometimes it's calculus 3. But you learn about partial derivatives, and what it really means is the partial derivative with respect to x says keep the other variables as constants. And then take the derivative with respect to x. So, for instance, for my function psi over here, this example, if I do the derivative with respect to x of psi, then when I look at this 4x plus 2y squared, the y thing, I'm just going to say, well, y, pretend like it's the number 5. So if I'm going to take a derivative with respect to x, the number 5 doesn't depend on x, so it's a constant, so I ignore it. So the answer would just be 4. The 2y squared just goes to 0. So that's the difference between a partial derivative and a total derivative. In a total derivative, we would have to assume that it's possible y depends on x. We may not know how it depends on x, so we would have to do maybe inductive derivatives or all sorts of things. But a partial derivative makes it easy. If I do a partial derivative with respect to x, then the y's are constants. If I do a partial derivative with respect to y, the x's are constants. And so this little curly version of a derivative, that's just a partial derivative. It means only take the derivative with respect to x. All other variables will be kept as constants for that purpose. Okay. What about these other things? The I, of course, that's square root of -1. That's the imaginary number I. I is going to play a huge part in quantum mechanics. Almost everything is going to have the imaginary number in it. And so you have to be very careful with the eyes. We're probably going to do a quick little homework thing, practicing with the imaginary number, how to do algebra with it, how to multiply by it, and all sorts of things. But just note, when you see I, the letter I, it means imaginary number, the square root of -1. And h bar, it's called h bar, is Planck's constant. But it's the one that's h, Planck's constant. Unfortunately, h is called Planck's constant, and h bar is also called Planck's constant, but h bar is equal to h over 2 pi. Okay. So when you look up the value of Planck's constant, that's going to be h. You take that number divided by 2 pi, and that's h bar. The reason for this is because when people were doing this stuff, a lot of their equations had 1 over 2 pi in it. And so in order to not have to keep writing this 1 over 2 pi thing over and over and over again, they just made a new symbol called h with a little line through it, called h bar. And that kind of sucked in the 2 pi piece. And so it just made the equations look neater. They didn't have to write 2 pi every time. So, with all that said, the momentum operator P all of a sudden is more complicated. When I act with the momentum operator P, what it means is you take the function, whatever it is, I call it psi here. You take a derivative, partial derivative with respect to the position, x, of that psi. Once you have that derivative done, multiply by minus I times h bar, and that answer is the answer to acting with the momentum operator. Now, there are, of course, lots more operators in quantum mechanics. We won't worry about them right now, though. Just note, these things are operators. Operators are very important. Why are they important? Every observable in quantum mechanics is denoted by an operator. So anything you want to measure, you have a system, quantum mechanical system, you want to measure something. I want to measure the spin of the electron. I want to measure its velocity, its momentum. I want to measure the time it takes to do something. Every single thing you could possibly measure, called an observable, has an operator associated with it. And so, in theoretical world, which is what we're doing, we're trying to do this theoretically, we're not in a lab right now. If we want to model the system and figure out, predict what will be this observable if I were to measure it, then what you're going to do is you're going to do some mathematical equation using the observable. So you take the function, let's say psi, I'll now call it what it is, the wave function, and we'll discuss this a lot in detail in the future. But basically what you could think of this thing as is all of the possible information about a system. So everything you could possibly know. Let's say we're doing an experiment. We want to measure something about a particular electron in an electric field. Okay? So we set up the experiment, we put an electron into this electric field, then this little thing, this wave function psi, is a function. I could write it down. It's a mathematical expression that has built into it every single piece of information possible about that system. So if this wave function has all the information I could possibly need, then, for instance, if I want to find or calculate a piece of the information, then I would act with my with my operator for that observable. For instance, what's its position? If I want to know where is the electron, that is, what's its position, then I would take my position operator, I would act with that operator on the wave function, and doing this mathematically pulls out the information about the position. And so I would have some answer sitting there. I now know the position. So you can think of it like this. Act with an operator on a function. That gives you some answer to the function. This is the answer. That's the operator. You apply the operator to the wave function. The wave function has all possible information. And when you act with this operator, the answer to your question is pulled out of the operator, and it's now sitting there for you to use. Okay, that's how you want to think about this operator stuff. Now, we're going to skip ahead just a little bit because all of this stuff we're going to delve into in detail, but I just want you to have a nice broad overview of what's going to be done. What we're going to do is build Schrodinger's equation from these operators. So the operators we need are, let's see, the position operator, which I already told you is just multiplied by x. The position operator, minus I h bar d by dx. What else will we need? Well, remember, what I'm trying to make is kinetic energy plus potential energy is equal to total energy. Well, what's potential energy? Operator. Well, because potential energy depends on what potential energy you're talking about, there's plenty of different potential energies. We're just going to call it V. V stands for potential energy. You're used to in physics PE, potential energy, but in real physics, potential energy is called V. Sometimes it's also called U, unfortunately. All right, what about kinetic energy? Well, first of all, kinetic energy is called T in physics. So we want the kinetic energy, which is called T. Well, what do we know kinetic energy is? This we want to work on a little bit. Let's work on it down here. Kinetic energy is let's do it, T, fancy. T is 1/2 mv squared. Right? Kinetic energy, 1/2 mv squared. But I don't have an operator for V, for velocity. The operator is momentum, P. So what I want to do is I want to take P, the momentum operator, which is mass times velocity, and I want to make it look like kinetic energy. How do I do it? Well, note, kinetic energy has a V squared in it, whereas momentum is just V. So if I take P squared, Well, now I have mass squared, velocity squared. Well, now I'm closer. I've got a v squared. But now I have too many m's. So if I divide p squared by m, then I now have m times v squared. That's really close. The only little thing left is this 1/2 sitting here. So if I divide p squared by 2, then this becomes 1/2 mv squared. And now we see, what is the kinetic energy? 1/2 mv squared. But I can rewrite 1/2 mv squared as p squared over 2m, where m, of course, is the mass. And in fact, when you go into graduate classical mechanics or advanced mechanics, this is something you do. You don't think of it as 1/2 mv squared anymore. You think of it as p squared over 2m, because there's things you could do with this. So, if I want the operator of this thing, well, there's the p sitting there, so this is the p operator squared. And then you just divide by these constants, 2 and m. All right. So now that I know the operators I need, let's make Schrodinger's equation. Schrodinger's equation, which is kinetic energy plus potential energy equals a number, total energy. Well, kinetic energy is P operator squared over 2m. Potential energy is V operator is equal to E. But let me write down what the P operator is. Let's look at it. P operator times P operator is P squared operator, right? P times P. So let's do P times P. Well, just one of them is minus I h bar d by dx. And then multiplied by another one, minus I h bar d by dx. All right, so what do we have? Minus times minus is plus. I times I, well, square root of -1 times square root of -1 becomes -1. So we have a negative. H bar times h bar is h bar squared. And then d by dx of d by dx, so it's the derivative of the derivative, is the second derivative. So when I have P operator squared, I can rewrite it like this. Minus h bar squared, second derivative. So I have minus h bar squared over 2m, still sitting there, this 2m right here. And now I have the second derivative with respect to x squared plus v equals e. And now the last step is to note that this thing that I just wrote is one big operator. It operates on a wave function. This thing gives rise to some information. What information? The total energy, of course, E. I want to know the total energy, so I apply this particular operator to the wave function of the system, and out will pop the energy of the system. So let's apply it. Minus h bar squared over 2m. The second derivative has to apply to something, so it will apply to some psi. And then this operator V applies to a psi. And what do we get? The answer, which we're looking for, which is the total energy, times psi. And now you have Schrodinger's equation. This is what's called the Time Independent Schrodinger Equation. because this form, there's a second form, which I'm not writing right now, but this form doesn't depend on time. It's like at a particular time, I've taken a snapshot of the system and I'm analyzing that snapshot. And at this particular time, this is the total energy. So this is the big guy. This is the huge, important equation which we're going to use for the rest of the semester. And you've seen how to get to it. All it is the total energy, the conservation of energy. But in order to calculate the energy for a quantum mechanical system, we have to do it through the use of operators. And so we had to take the total energy equation and replace all its variables with operators. Once we have all the operators sitting there, well, now it's easy. We just apply the operators to the thing which can give us the answer, the wave function, and we have everything we need. Now, what we're going to do is we're going to use this for certain particular systems and try to get answers. You know, we're going to pretend like we have a particular experiment. We have an electron trapped in a particular box. And what's its momentum? Or what's its position? Or we're going to ask these questions and see if we can calculate them. And what we're going to see is over the whole semester, and in fact, pretty much everything you ever do, there's really only 4 systems we can do by hand and write down the answers to. Everything else has to be done through the use of computers, approximations, models. We can't get the exact answers, but we can get very, very close. And the reason is because the equations we're going to be writing down for almost every system in the world is impossible to solve by hand. Some of them we can, and those are the ones we're going to work on. Everything else, we have to use fancy techniques. And that's what makes quantum mechanics difficult. The equations are very difficult to solve. But some we can solve, and they've been solved before, and we're going to learn how to do it. And those are the ones we're going to concentrate on. So, I hope this is understandable. I wanted to give an overview. Obviously, each of these little things I've talked about, there's a heck of a lot more to them. But I didn't want to get into it because I didn't want to have things get very confusing. At the end of the day, what I want you to know is, let's look at what we did. Quantum mechanics is going to use differential equations. In fact, the thing we wrote down, Schrodinger's equation at the end, is a differential equation because it's got the little derivative sitting there. We make use of operators. Those operators allow us to take the function, which has all the information hidden inside of it, and pull out whatever answers we need. So, the interesting thing is, when there is an observable we want, when there's something we want to measure, we need to know what is the operator for that thing. If we don't already know the operator, we have to figure it out. But, of course, quantum mechanics has been happening for 100 years now. We've figured out pretty much every operator in existence. So all we have to do is apply the operators to the wave function, if we have it, and that will give us, if we can solve that thing, will give us the answer that we're looking for. What's the big equation that we're going to work on? The big equation is called Schrodinger's Equation. This one I wrote down is time independent because there's nothing in the equation that has to do with time. There's another form where the right side has a derivative with respect to time in it. Don't worry about that for now. This is the form we're going to use to do a lot of things right now. So this is the one I want you to worry about. What are we going to do in the future? We're going to use Schrodinger's equation to calculate the wave function. Because that's going to be the thing we don't know. Obviously, I've made it sound easy where I say, hey, look, take the wave function, apply an operator, you now have your answer, which is true. The problem is finding the wave function which has all the answers built in. They're not just sitting there when we build our experiment. It doesn't just talk to us and tell us what the wave function is. We need a way of solving it. And Schrodinger's equation allows us to solve the wave function. Once we know the wave function, we can get our answers. So, what we're going to do, we're going to set up particular examples. The first big one being what's called the infinite square well. It's the easiest one to work on, or second easiest. The easiest is the free particle. I'll do that one too. And we'll see how to use this equation. It's going to take us knowing about derivatives, knowing about integrals. We have to know about complex numbers and imaginary numbers, and how to solve differential equations. If you're not good with this stuff, don't worry. I'm going to do my best to teach it to you. And what you're going to find is the way we solve differential equations in physics is not always the same as you learned in math. In physics, we do things a little differently. We solve things in not so fancy a way. Brute force methods, easy methods. We don't learn the fancy, formal, mathematical methods. I mean, we do learn them, but we try not to have to use them because they're easy to forget. So we're going to walk our way through these, but just know, coming up will be the first example, the infinite square well. Also, I will be putting out an assignment about complex numbers just to make sure you understand how to work with complex numbers. And we'll go from there. So I hope this has been interesting. I hope it's understandable. And until next time.